of expander. So epsilon expander graph, and this was something of the form x equal v vertices and edges, so that for every subset A of V, which is neither the full set or V, the A bar divided by the minimum of A, the size of A, and the size of A bar is bigger than some epsilon. And actually, we call the Chigger constant of X is really the minimum of that over all A. Right? So this, I just would recall this Chigger constant of a graph. And now we mentioned that this is equivalent to a spectral gap of the adjacency matrix. Then we went to the I-dimensional expanders and Ramanujan complexes, and those were higher dimensional versions of this notion. Now, in fact, I spent a little bit more time on the Ramanujan complex because there is kind of a one natural extension of the notion of Ramanujan graph. So I recall Ramanujan graphs are those graphs for which you have the optimal spectral gap, and we have such a version, I-dimensional version. What I really want to mention and to recall that they are obtained like that. Such an X were obtained as taking SL n QP, SLn over the p-adic number. We divide it by a maximal compact subgroup, which is, say, SLn ZP. So this is kind of the p-adic analog of the classical symmetric spaces a la Cartan for simple Lie groups. This is the so-called Brouwer-Titz building. And when we divide it from the other side by a lattice gamma in G, a lattice is a discrete, in our context, it's a co-compact lattice. We are getting a building, a discrete object divided by a group gamma. So this is a simplicial complex, but it's compact because this quotient is compact, so it's a simplicial complex, which is compact. Discrete plus compact means finite. So we have a finite that. Okay, so now we are ready to Gromov problem. So Gromov problem so maybe let's first set some notation. X is a simplicial complex. Now we are going to so what is really X? Let's say finite. I think we will work only with finite simplicial complexes. Well, the building is an infinite one, but we will work today with finite simplicial complex. So what we mean by that, I want really to set carefully notations now. We can think of it in two ways, either as in a very abstract way, but of course it has also a topological, or if you want, even geometric meaning. So X is a collection of subsets of V. V is also a finite set. This will be the vertices of X, such that if, say, sigma is in the collection and tau is a subset of sigma, then tau is also in the collection, right? It's closed under, the collection is closed under that. The dimension of such, so these are called cells, the elements in the collection called cell. The dimension of sigma is sigma minus 1. And now the dimension of X is the maximum over all sigma in X of the dimension of sigma, and we will assume that it's pure. Pure means that X is pure, means that every tau in X, there exists some sigma in X of dimension sigma equal to the dimension of X, the top dimension, and tau is in sigma. So like every cell is inside a cell of maximum size. I'm putting this notation because I will use it later on. Now, Gromov, I'm now changing the history a bit. I'm giving you names which Gromov didn't give, but that's the way we are thinking about this now. The definition, actually, these things I want to keep. So I will leave it here. This I will erase soon. The definition is that we say that X is epsilon geometric respectively topological expander if for every map from the vertices V to R to the D, D is, maybe I should call it, D will be always the dimension of X. If we have a map to R to the D, then for every extension F tilde from X to R to the D. So now you are supposed to think of X not in the formal way I define it here, but it's clear that X has is really an object. You know, we can fill up if we have 2 points, we fill it by an edge. If we have 3 points, we fill it by a triangle, etc., etc. So we can talk about maps from X. So now for every X from X, affine, basically there is a unique extension. So for every extension, F tilde, extension of F, respectively continuous, there exists a point Z in R to the D such that F to the minus 1 Z meets at least epsilon of the top cells of the cells in XD. Okay, this is a D-dimensional expander. I want to recall I showed it in the colloquium, but I promised that the lectures will be independent of the colloquium. Then I mentioned there that there was a theorem started by Borush and Furedi, and then for dimension 2, and then by Barani for every dimension, that if X and D is the complete D-dimensional simplicial complex on n vertices, we think of it now as n going to infinity, and we have a family of infinitely many. So we take all subsets, you take n point, and you take all subsets of size at most d plus 1, right? This will give you dimension d. Then a Barani theorem is really equivalent to say that X and D are some constant C, D geometric expanders for the same CD, and the amazing theorem of Gromov that they are also topological expander. And I made a picture why this is so amazing, because it means that if you put something like n points in the sphere, and like even in dimension 2, sorry, and you start to write all possible triangle among them, but you can make the triangles not by straight line. You can make the triangle by, I had some color. If you take now the points, and you know you want the lines between them to be all very narrow in any way you want, somehow nothing will help you. You will get a point which is covered by some constant fraction of the possible triangle, which is kind of an amazing results. Very surprising, at least to me when I saw it for the first time. I have to say that this is not. I was also so much amazed by the method of proof. Though some people there told me that it's not, that there are people use this kind of methodology for some of the method. Anyway, so Gromov says that these are expander. Now, first of all, why the name expander? Actually, he didn't call it expander. We started to call this expander. So let me just make the observation in dimension 1. In dimension 1, a simplicial complex is just a graph, right? So in dimension 1, I claim that expander implies a topological expander, and of course this implies geometric expander, right? Topological expander is much more. Why? Because what we have to prove, right? We have a map from the vertices. We have a graph. We have a map sending the points to R in some way. I don't know how. Yeah, right? I have points on the line, and then we have to prove that there exists a point. And now we extend it to the graph. We send the graph to the line, and we have to prove that there is a point such that many edges are crossing that point. So take a point Z here, such that half of the vertices were sent above it, half of the vertices were sent below it. This divides the graph, the original graph, into two sets of equal size, more or less. And then, what is expander? Expander means that there are many edges. So this is like half of the graph. There are many edges going from A to A bar, and that's mean that they are topological expander. Now, I made this remark in order to stress that it's not, the opposite is not true. Topological expanders are not necessarily expander. Here is an easy counterexample. Take a huge graph, which is an expander, union with a small graph, which we don't care about it. So that graph is not even connected, the union, right? It's not even connected. But it is still topological expander, because who cares about the small graph, right? This condition is really, this condition is enough that most of the edges are on the big graph, on the big connected component. So the fact that we have another connected component is irrelevant. And I'm stressing this because it will come up later on in a slightly more delicate way. So, sure.
So you have the dimension of simplicial complex, and then you have a D in the definition of an expander, and I'm confused about.
The same.
They have to be the same.
Right, right. You have
a one-dimensional simplicial complex in any D-dimensional space, and you just have a geometric graph,
Right. I mean, okay. I mean, you can ask, there are many questions that can be asked here, like what is the minimum that you can embed? Start with an expander, topological expander. Can you embed it in dimension which is maybe d plus 1? Or usually it goes like 2d plus 1. There are, there are various theorems about that. You know, you have a manifold dimension d. Can you embed it in RD? So I'm not touching this type of question, but it's kind of related. Anyway, I want to discuss now the Gromov problem in his seminal paper where he proved this. He proved also the spherical building, finite spherical buildings are a topological expander, etc., etc. But all of them are not of bounded degree. And if you really think about dimension 1, to prove that the complete graph is an expander is triviality, right? The whole point of expander is to prove that there exists bounded degree expander graphs such that every vertex is inside a bounded number of edges. So he put forward the questions, are there bounded degree? So I can write it here, Gromov's problem. I should say problems. 1, are there, maybe I put the 1 here. 1, are there, bounded degree geometric expander. This is problem 1. And problem 2, topological expander, which is, of course, more difficult because every topological expander is geometric expander. And few years after that, a paper came by Jacob Fox, Gromov himself, Laforgue, Arber Asaf Naor, and Janusz Pach, all the great names of the area, and said there exists, for every D, there exists bounded degree geometric expander. And they gave actually 2 proofs. Asaf told me at some point that they gave several more proofs, but they gave 2 proofs. One is random. They look at random. Let's think let's think for ourselves what we mean by random, 2-dimensional simplicial complex of bounded degree. Right? Let's think first, what is the random, when we say random model, okay, some people may say, okay, you don't have to define, just take all of them, the possible, and ask what the probability. But it doesn't really work like that, right, Noga? Usually you have a model. What is a model for random k-regular graph first? Actually, there are several models. I think it's known that they're equivalent, but it's a theorem that they're equivalent. And one is take n points and take, let's say that n is even. Then, how do you call it? Matching. Take matching. Namely, you take random, you divide them to n over 2 sets of 2 elements and put edges. Now you do it once, you do it twice, and then you do it k times, and then you get a model for k-regular random graph. Now you can do exactly the same thing in dimension 2. Take n to be, say, divided by 3, and then you divide the set into subsets of size 3, right? And then you declare them to be triangles, and you do it k times, right? So this will be, that's the kind of random model they use, and they prove that they are geometric expanders. And the second one, they use the Ramanujan complexes. I have to be honest, I didn't know anything about this area. Just somebody told me, oh, look, they're using your Ramanujan complexes. So I started to look into this subject. So they took those Ramanujan complexes and used I have to admit that I didn't really explain in details the properties, but there is a kind of a spectral gap involved there. They use this, and they prove that they are a geometric expander, but they left open the problem of topological expander. Now I want to stress random, as I described to you, are not topological expanders. This is still one of the major open problems in the area. Is there a model of bounded degree simplicial complexes which are topological expander? In that model, they are not.
I think the random you described, I think, is not so good because maybe you want bigger sets than 3 and you want to take all the, because otherwise every pair will be contained in a single.
Right. That's what I was about to say, that's why it's not good. But so so it might be, you're right. So what Noga is suggesting, to take another model, take like a set of 4, make a random 4, and take its two skeleton.
And I think that this is what they do, actually.
This is what they do?
Because I think that if they don't do, every pair is contained in a single triangle, and then it's...
I tell you the truth, I haven't looked at it for 10 years, but okay. So even this one is not. This is stronger one, and it's still, no, but I think even this is not topological, no? Right, so anyway, we don't have, to be honest, I want to make a conjecture which is not, it's kind of a moral conjecture rather than a mathematical conjecture. I think that there are no such models.
Wishful thinking.
Because, no, because, and let me explain. I mean, I'm thinking about the Lie theory situation. The Lie theory situation is that in the low dimension, in dimension 2, you have Teichmuller space. You have many, many surfaces. On the other hand, in higher dimension, in higher rank, you have the rigidity, which says that the lattices which exist with the structure are very rigid, and only those which kind of enforce on you by arithmetic. They're kind of gems in the sky and nothing that. So somehow it might be that these two problems are related, even though I'm not sure, and even this is, what does it mean to say there is no random, it's not a mathematical statement. I even don't know how this could be stated. Anyway, the story with topological, and really with topological it was not clear, it was not a conjecture of Gromov, it was really a problem of Gromov. In fact, I talked with him and he told me that he didn't know what to think about, if there exists or not topological. So the news is that there exists theorem for every D, there exists bounded degree topological expanders. Now this was proved for D dimension 2. It was proved by Kaufman, Tali Kaufman, David Kashdan, and me. And for all D by Kaufman and Shayevra. it was a fantastic generalization because in a way, Evra is a very modest person. He said, oh, well, we just did what you do instead of doing T, but that's not true. He kind of understood the tree. How do you say? He saw the forest behind the tree. Because our paper was 40 pages and they did it with 25 and much more general. But in both cases, it's true that the kind of the point was similar. So I guess everyone would think, if I'm talking about this and I prepared Ramanujan, so what is the result? The Ramanujan complexes are that. This is still an open problem. This was proved in both cases. It was proved in the following method. It was proved by proving that if x, or maybe call it y, if x is a d plus 1 Ramanujan complex, and P very, very large. I'm hiding how large it should be, because if you really want to go over the proof and you ask how large P should be, it's probably more than 10 to the million. But the combinatorial people still call it a bounded degree, even though the degree really is enormous. We really don't understand yet the problem if we can get it with reasonable degree. If y is the d plus 1 Ramanujan, then x equal the d skeleton of y is the topological expander. That's kind of strange. What you do, you take the original Ramanujan complex and you delete the top dimension and you stay with dimensionless. Because you do it for every d, then it's give a full solution to the problem of Gromov, but I have to say that we still don't know if d-dimensional Ramanujan complexes are topological expander. But the rest of my talk, I want to the proof of Gromov and the proof of this are fairly complicated. I will not go to that. I want to open a zoom on one item which comes up in a proof, which is a coboundary expansion. And this is what I'm going to stress in the rest of my talk. Now, because that will show you the connection with the other problems I'm going to discuss. So let me give, because I promised that I will try to be self-contained in the sense that everyone can understand, not that everything is proved. Let me give a 3 minutes course in cohomology. Okay? So, but in cohomology mode 2, which is much easier than ordinary cohomology. So let me set up the standard definition. So I set up here now think of a simplicial complex in a very formal way, just in the way I wrote it over there. And let's denote Ci x f2 to be all the functions from xi to f2. I don't remember if I said here. So xi is simply the set of all cells of dimension I. Okay? This is Ci. So all the function f2, you can think of it, because it's just 0, 1, you can think of it as characteristic functions on the set of I cells. So if you want, you can think of it as, of every such f as a subset of the cells. Now let me define right away. It will be convenient to give a norm to such an f, this will be simply the number of sigma in xi, so that f of sigma is not 0. So if you want, if you think of it as a subset, it's just the size of the subset divided by the total subset. It's convenient to give some norm. You can take other norms, but I'm not going to go to that. Now let's take Ci to Ci plus 1, the coboundary map. What is the coboundary map? We take a function. I should be careful and write delta I, but later on I will ignore the I. Delta f of sigma. So now sigma is a cell in xi plus 1, right? I have to tell you how this acts on sigma. So this is simply by summing up all over all tau inside sigma on all the walls of sigma, right? The dimension of tau is I of f of tau. It's so much easier to do it in F2 because we don't have to think about signs, etc. And therefore, and now this is clearly a linear map, and this is a well-known exercise that you have to do it once in your lifetime, not more than once, and do it here because over F2 is really trivial, and that delta after delta is always 0. If you see you arrive to each cell 2 steps above in 2 ways, and they cancel each other. So, and therefore, we can talk about Zi be the kernel of delta, to be precise, kernel of delta I, and we call it the co-cycle, and the co-boundaries is the image of delta I minus 1, if you want to be precise. And because of this formula, Bi is inside Zi, and Hi, Zi mod Bi, this is the cohomology of X with F2 coefficients. Okay. Now, here is, let me give, I know that this is recorded, so those who never saw it, let me give you one exercise that X is connected if and only if H0, H up 0, because it's cohomology, not homology is equal 0. Okay? Now you have to think about what is X0, because I forgot to mention that, but you should know that the empty set is always a cell, right? Because it's closed under that, and it's a very respectable cell in the complex. It's a cell of dimension -1, and we have to remember that it exists and there is a map from here. So think about it when you solve this problem. Okay, I will continue now with something. I'm going to write a very formal definition, which is in the first sight, it's very technical, and the motivation is not at all clear. If you look at it, maybe you want to get out from the room. You don't want to study this type of object. But what I will try to convince you that this is an extremely important and useful property.
In F0, F2 or 0?
What?
F2.
Everything about F2.
No, you say X is connected if and all H0 and F2. Do you consider?
If and only if the vector space, so it's really if and only if Zg0 is equal to B0. B0, think about it, B0 is,
1 point.
what?
Just a graph, trivial graph, 1 point.
No, why? No, B0 really B0 is really the constant functions, and Z0 is, what is Z0? Is all functions that the delta of them is equal 0, right? Which means that on every edge they give you 0, which means,
You see, because he has a C minus 1. And said, remember the empty set is in every set. So it's really the reduced cohomology.
You can say empty set as a.
Of course, I said, the empty set, I said before, it's a very respectable member of the, it's a very respectable. By the way, here is, and I want to stress, so what is x to the minus 1? So usually when I ask people, they say the empty set. No, this is the set containing the empty set. Anyway, let's go because I don't want to, but let me give you the most important definition of today's lecture, and this is coboundary expansion. And then we'll do coboundary expander. So you see, I warned you in advance, this I-dimensional expanders is kind of, there are too many suggestions to what we should call I-dimensional expanders, and they are not equivalent. You know, we already saw a few of them. Okay, so now I'm going to define the following. Let's define HIB, if you want, HIB of X is equal to the minimum of delta of f, the norm of delta of f. You remember there was a norm here which was essentially, where is the norm? I erased it? Right, this is the proportion, this is the size of the support normalized, right? So I take d of f divided by the distance of f from bi. And this is over all f which are in ci, over all the cochain, we call them cochain in ci, but not in bi, right? We cannot take in bi because then the distance will be 0. Right? I take now what I call the distance between f and the coboundaries. This means this distance between f and bi is the minimum over every b in bi of the norm of f minus b. Okay, looks very strange. But I want to convince you that this is a very good, an excellent definition. A first proof that it came up completely independently in two works, one by Gromov and one by Linial and Meshulam. They both came, well, they maybe up to normalization that one used and the other not, but that doesn't matter. They both look at exactly the same. Without calling them expander, without both of them, I think Gromov had in mind some expansion. I think Linial-Meshulam didn't really thought in this terminology. I'm kind of going backward in the history. So in order to convince you that there is something good here, let's do a quick exercise. I will start to do it for you. And let's compute, let x be just a graph. Right? And we'll ask what is h0b of the graph. So what we should do, we take a function on the vertices, right? Let's ignore the normalization for a second. We take a function, what is f? F in C0 is some characteristic function on the vertices. So this is really some subset, right? So I'm taking the size of this, and now, sorry, what is delta of f? Now, delta of a function, characteristic function of A, on the delta of it on the edges, for every edge, I take f on the origin minus f of the tail, right? Which means if they are equal, it's 0, because characteristic 2. I get a contribution if they are different. If they are different, it exactly means that I am that the edge is here in A, is between A to A complement. Okay. Now, what is the distance of a function? So the top is, I'm ignoring normalization. This is basically EA, E bar divided now by the distance to the boundary. What are the boundaries? The zero boundaries, because the empty set is are the constant function. There are only two constant functions, either 0 or 1. So 0 means that this is a characteristic function which gives of the empty set, and 1 means that it's characteristic function of the full set, right? And I take the minimum between the two. The distance to the 0 and the distance to the full is exactly this. It's the size of the set or the size of the complement, right? So basically, up to some normalization, this is the classical Shiger constant of x. So you see that there is something here. In particular, maybe there is justification to call it expander. Now, I want to say to some people who prefer spectral gap, let me give you another exercise. I will not write it. Think about this definition in terms of spectral over R. Think about it over R. What is delta of F and what is this? And if you think about it over R, you'll see that what you get is exactly the spectral gap. So this is kind of taking spectral gap over F2. Think about it. This is the kind of a nice, good exercise. Okay. Now, actually, let me explain first why this definition, because I want to make a big deal out of this definition. It will come again and again in the next two talks. So they are going to be very boring. I'm boring you, because they are going to get to this definition, which looks boring. I'll try to do my best to convince you that it is interesting. So let me explain first of all why Linial-Meshulam were interested in that. Linial-Meshulam took on themselves the task of generalizing the Erdős-Rényi theory of random graphs. You know, Erdős and Rényi initiated many years ago. I hope you're not going to jump. It's not that boring. Erdős and Rényi introduced the theory of random graph. What was their model? They took endpoints and said, now for every edge, I include it with probability p, and p is something between 0 to 1, and exclude it with probability 1 minus p, and we get some graph, and they study the properties of such random model of graphs. Now, their first theorem, they asked themselves, for what p the graph is connected. It's clear that it's for p equals 0, it's not connected. For p equals 1, it's a complete graph, so it's connected. And they prove that there is a threshold. Threshold means that, without being too precise, that if you take p to be log n divided by n, then before that, it's not. If you are less than 1 minus epsilon this, it's not connected. If you are above the threshold, you are connected. Now, Linial-Meshulam wanted to establish such a theory for two-dimensional simplicial complex. Now, what did they say? They took start with again, you take the vertices to be say the number between 1 and n, and all edges. So you take the complete graph, And then you take a triangle, you take a triple of points, and with a probability P, you want to say, is it, do I put the triangle there or not, right? Okay, what's the first question to ask? Is it connected? Of course it's connected, because we started with a complete graph, right? But they said, connected, you remember the exercise I gave before, and unfortunately I erased it. Connected for graph, dimension 1, is equivalent to vanishing of H0. So they said, let's study for the two-dimensional when H1 is 0. And they prove a threshold in dimension 2. They prove a threshold. It was very beautiful. It's where P0 is equal to log n over n. Later on, Meshulam and a student of him, Wallach, generalized this model to d-dimensional. Again, they took the complete d-1 dimensional complex and then decided on every d+1 points whether they are in or outside, and they prove the threshold for the vanishing of h d-1 x of d. The threshold is for P0 equal d times log n divided by n. It's very beautiful. Actually,
Other HIs
what?
in higher dimensions, do they have that understanding of the other Betty numbers, the other cohomology?
Yeah, I think you can deduce from that because they vanish, because it's kind of a full skeleton.
They're all zero.
Yeah, but that's the complete model. That's not so difficult. I mean, if you will go to a bounded degree, then yeah. So that's a beautiful theory. But now, in order to prove this, they invented this in order to prove these results. Let me explain why. Because look at the following observation. If HIB is equal to 0, then it's not equivalent. I'm not claiming. Then HI of x is equal to 0. Why? Because if this is positive, now we are talking about finite simplicial complexes, right? So it means that every, you see, what does it mean that the cohomology is not 0? That there is some f which is not a coboundary, but it is a cocycle. Delta of it is 0. So if there is such an f, so the distance between f to bi is some positive number, but then delta of f is 0. So if the cohomology does not vanish, then this, if the cohomology does not vanish, then hi will be 0. So if hi is not 0, it's a positive number, then the cohomology vanishes. This is a trivial observation. But somehow, to analyze this, it was more convenient to analyze this than to analyze hi. If you think about it now retrospectively, and the way we think about now, go back to Erdős-Rényi. Erdős-Rényi proved that the threshold is making it connected. But if you check, they really proved that the threshold make it expander, not just connected. So also here in a minute, we are going to define expander in a way that their proof really make it an expander in the threshold. By the way, to guess the exact threshold is not so difficult if you think about the coupon collector problem, if you want to think about it. But I will not stop for that because I want to go to my main line of talk, and this is to go back to Gromov. Why Gromov did it? Because what Gromov really proved, and I think now I can erase this, I don't need it anymore. What Gromov proved, he proved, that's kind of the main theorem of Gromov in some sense. He proved that if there exists an epsilon greater than 0 such that HIB of x are more than epsilon for every I between 0 and d minus 1, then x is epsilon prime for topological expander. Okay? That's what Gromov proved. So nowadays, to this condition we called coboundary expanders, right? And I already define you topological expander, right? So coboundary expanders implies topological expander, not vice versa. So what do you think we have proved? That the Ramanujan complex, the d minus 1 skeleton of them, is that no. Not only that we didn't prove it, it's not true even. So here is a warning. Ramanujan complexes are not, usually, I mean, maybe some of them are not coboundary expansion. Why? Okay, because if they would be coboundary expansion, then the cohomology should vanish, right? That's what we said before, when we justify the Linial-Meshulam interest in that. But, well, we learned, I mentioned it in last lecture, that the cohomology of the Ramanujan complexes, and even more general, vanish over R. But it definitely does not vanish over F2. It does not. Okay? At least in general. I'm not saying that you cannot.
The Garland argument doesn't work.
What?
Garland.
No, absolutely not. You use positivity in a very strong way. It does not. I mean, it's not true, you see. Right. The positivity. There is no positivity there.
He's really like Matsushima.
Yeah. Right, yeah. Okay, so what instead? Well, this was very frustrating, but there was a way out of it. Here is a theorem. Here is a theorem which was proved by, it's a kind of relaxation theorem. It's kind of, I mean, this theorem was proved, it was kind of, we ordered this from Uli Wagner, and it was proved by him and Daughter and Kai. It says the following. Okay, now this is coboundary expansion, okay? Let me define cocycle expansion. You probably can guess what will be the definition. Cocycle expansion will be do exactly the same thing, but instead of doing here bi, do zi. So we and also here, and I don't want to erase it, just and also here take zi. Just take functions which are outside the cocycles, and count and divide this by the distance to the cocycles. Okay. You can guess that if you have if all of them are more than epsilon, blah blah blah, how do we call it? Instead of coboundary expanders, cocycle expanders, right? So they prove, but let's careful. They didn't prove the cocycle expanders are topological expander. That if X is a cocycle expander, cocycle and expander, and large cosystal. What does it mean? Cosystal. This means that there exists some number, I don't know, theta, positive, such that for every f in zi, the norm, and zi not in bi, then the norm of f is more than theta. You remember, I give you an hint to this theorem. I told you that, you can get topological expander without being connected, without being expander, because you can take a small part. So kind of the I-dimensional version of that is that you want cocycle expansion and you replace it by this large consistol.
It still depends on I.
What? For every I, the same theta for every I. So that real theta, so that for every I, you have this property, okay? And so then it is topological expander, and that's what we proved. And now, that's prove the results of, and let's give the solution to the results of Gromov in the next. So that's really what was proved. When I said that what Kashdan, Kaufman, and me proved for dimension 2 and Evra and Kaufman in all dimension, that's really what we proved. That this criterion is satisfied. What?
So you mean the topological expansion constant depends on the
On both.
cycle constant and the theta.
Right, absolutely, yes. Now, I want to mention that Gromov really asks kind of two questions. Are there I'm translating you to my language. Are there coboundary expanders? And are there topological expander of bounded degree? Everything of bounded degree. So this solves the topological. Coboundary expanders is still open except of the case D equal 2 that Michael Chapman, who is here, and I are now writing a paper that we can solve it in dimension 2. But for that, for a crazy reason, we have to go to the symplectic groups rather than SLN because of the affirmative solution to the congruence Savu property and blah, blah, blah. But it's kind of a little bit pretty spatial, and we don't know yet the answer.
Do you know about the vanishing or non-vanishing of the cohomology with two coefficients for these?
Of what?
Of Ramanujan complexes.
So I know, in fact, already in 87, I wrote a paper. I didn't know anything about the subject, but for some reason I was interested. That translating it to this language proves that for every linear group, finitely generated linear group, you can find infinitely many subgroups of finite index, and that H1 gamma F2 is not 0. Okay, so in a way that what Michael and I now proving that in some spatial cases, and we use fancy material to show that there is a sequence where H1 is 0. And then using Evra, and so somehow we get coboundary. Okay, I want to mention to take, because I started even 4 or 5 minutes late, I will take another 2 minutes. Because I said that the coboundary expander have two motivations. That's true. That's what motivation to the expander. But in retrospective, there is one even more important application, which started with a little paper of Kaufman and Mai, which I must say is a completely trivial paper, but it became maybe my most influential paper. Observing the coboundary expansion is a property testing in computer science. So let me explain just why, and the next 2 lectures will bring this to the front. Why this is a property testing? What is property testing in computer science? Property testing in computer science is, I give you, there is some collection of something, let's say vector space, and there is a subspace of it, or a subset of it. You pick up an element, a vector, let's say a vector from the vector space, and I ask you, is this vector is in the subspace? Okay, if the subspace is defined by many equations, so I tell you, naturally you go and check the equation. But no, I don't allow you. When I give you this F, you are allowed to read only few bits, bounded number of bits out of the vector. And you have to decide whether it is in the subspace or not. Of course, this is impossible, because if one bit steered, you have to, this is a random algorithm, and you decide with a high probability whether it's inside or at least very, very close to that. I will define next week precisely. But I want to point out to you that this being coboundary expander is a property testing. Why? Property. Take F to be a cochain. And I ask you, okay, so this is a function defined on the I cells. I ask you, is it a boundary? Is it a coboundary? Is it inside BI? So here is the random algorithm. Pick up a random I cell, and check delta of it. When you check delta of a cochain, you just check the function f on the walls of E, on the walls of this, namely a bounded number of bits. You read a bounded number of bits, and answer yes if it's 0 and no if it's not. Now, what does it mean that if with high probability you answer yes? It means that most of the time delta f is 0, which means that this is a small, the norm of it is a small number. The norm is exactly the probability that it is not 0. If this is small, and if this is bigger than some epsilon, then this must be small. Right? Otherwise, if this is big, you won't be more than epsilon, which means that f is nearby a coboundary. So this is so every theorem about coboundary expansion is a computer science theorem about property testing, right? That's the message that we will start next week the talk with, okay? Thank you.